Hello, this is Tzvi Rosen. I'm going to speak today about factor groups, more popularly known as quotient groups, but known in Herstein as factor groups. We'll pick up where we left off in our discussion of normal subgroups in class and go from there. So let's start by defining a normal subgroup. So let's say we have a group G. We have G a group, and a subgroup N in G. We say that N is normal if AN A inverse is equal to N for all A in G. Okay, and this we've spoken about is called the conjugation by A. So conjugation by A preserves the normal subgroup. It doesn't mean that the conjugation doesn't affect the elements of the subgroup. So you might have AN A inverse is not equal to N, but it has to be equal to some other element of the normal subgroup. So this is possible, but it still needs to be in the subgroup. Okay, so as a set, the set remains equal, but each particular element in the set might be sent to some other element of that subgroup. Okay, equivalent description. N is normal if every left coset is a right coset. Okay? And we saw both of these definitions in class. Okay, so let's look at an example group, which I don't believe we've discussed before. This is the group of unit quaternions. And this is a special group with respect to its normal subgroups, and we'll talk about that. So the way the quaternion works, we have plus and minus 1, plus and minus I work the way that we're used to them working in the complex numbers. But we have j squared and k squared, like I squared, are also equal to minus 1. And ijk is equal to 1, which implies in particular that ij is equal to k. Sorry, that ijk should be equal to minus 1. Let's just take ij is equal to k. jk is equal to I, and ki is equal to j. So this defines multiplication on the quaternions, and any one of its elements generates a subgroup. Okay, and in turn, every subgroup is cyclic. So in particular, besides I guess the whole group isn't cyclic. The whole group isn't a cyclic subgroup, but every proper subgroup is cyclic. So there's minus 1 and 1. Well, let's just draw this as a lattice. We'll discuss containment at each level. So Q8 is our group. Obviously, there's the group which just contains the identity element, which we'll call 1. And then there's a group that has minus 1 and 1. Under multiplication, minus 1 squared is 1, 1 squared is 1. Now, there are a bunch of other groups in between here. So, in particular, you have the group generated by I, the group generated by j, and the group generated by k. And on top of those, you have the whole group. Okay, so every one of these edges going up indicates containment. So minus 1, 1, that subgroup is contained in the subgroup generated by I, because I squared is minus 1, and I to the fourth is 1. Okay, so an interesting thing about all of these subgroups is that they're all normal. Okay, so the subgroup generated by I is normal in Q8. Okay, and because I, j, and k are equivalent up to symmetry, so this also implies j and k are normal in Q8. And let's see why this is true. So if we have the set I squared, let's put 1i minus 1 and minus I. So if you want to think about what happens when we conjugate by any other element of the group, so we know that the inverse of j is minus j. So let's conjugate by that. See what happens when we multiply it by I. Well, we get minus j times I times j. ij is k, so this is minus jk. But we know that jk is I, so this is minus I. Note that this doesn't fix I. It changes it, but it still sends it to something else in the same subgroup. Okay, by the same token, if we take minus k times I times k, we'll get minus ki k equals minus jk, replacing the ki by j. And minus jk is also minus I. Okay, so when we conjugate by either j or k, we get another element of the same subgroup. This indicates that the subgroup is normal. What's interesting is that even though every subgroup is normal in this group, it's not an abelian group. And the converse happens to be true. Whenever you have an abelian group, all subgroups are normal. But as we can see from this example, all subgroups are normal. And minus 1 and 1 commutes with everything, so we don't have to check that. This is the center of Q8. All subgroups are normal, but Q8 is not abelian. Okay. Now let's consider the dihedral group D8. I've also called this D 2 times 4. This is the group of symmetries of the square. So we have there's rotation by 90 degrees, and there's reflection across some line. Let's use this line. So if this is S and this is S, this is R for rotation. So we know obviously that R to the fourth, when you rotate it around 4 times, you get back to where you started. That's the identity element. When you flip it across that line, then you flip it again, you get back to where you started. And also, when I rotate it once 90 degrees, okay, so we can look what happens when we first rotate and then we flip. So it's as if we had flipped and then rotated it in the other direction. Okay, so this is the same as rs cubed. Sorry, r cubed s. Okay, so this is going 270 degrees, which is the same as going 90 degrees in the other direction, and after flipping. Okay, so there are a few subgroups here, but one subgroup I want to look at is the subgroup generated by R. So if we look at R, R squared, R cubed, R to the fourth, so no reflections involved, just rotations. Then this is a cyclic subgroup, and it's contained in D8. And this is actually a normal subgroup. So in order to prove that it's normal, we only really have to check with S, because S is the only S is the only element, or it's a representative of the only other coset. Okay, there are two cosets here. And so just to confirm that, if we take SRS, this is equal to r cubed s squared, which is just r cubed, so that's plainly in the subgroup, okay, which is in R. A fact that's true about subgroups in general, if the index of H in G is equal to 2, and this is also written as G colon H equals 2, then H is normal. And so this is satisfied by the subgroup here, and actually also by the subgroup on the previous page. And the reason for that is there are only two cosets. There's the subgroup itself and everything not in the subgroup. So because the subgroup itself is obviously a left coset and a right coset, then the other because left cosets and right cosets partition your group, the same must be true of the complement of the subgroup. Okay. Idea of proof, just include this in one word. Left cosets equals right cosets. Okay. Okay, and this is a couple of other things where we have facts about normal subgroups. If you have G abelian, and we have a subgroup H in G, that means that H is a normal subgroup. Okay, so all subgroups of an abelian group are normal. The reason being quite simple, that GH, G inverse, this is the set of GH, G inverse, H and H. But this is an abelian group, so you can flip-flop the G inverse and the H. Apologies. G inverse of times H for H and H. And that's just H, right? Because this gives you the identity. So that's one thing. The other thing, Z of G, you'll recall, is the center of the group. This is the set of elements H, or let's call it X in G, such that AX, such that for all A in G, AX equals XA. So here, so we claim that Z of G is normal in G. And the proof is that if you take A Z of G, A inverse, what do you get? This is equal to the set of A X A inverse for X in Z of G. But this set isn't just fixed by, it's not just, the set is not just fixed, every element is fixed, right? Because if AX equals XA, then AXA inverse equals X. This is just the set of X in Z of G, so it's just Z of G. Okay. So these are two additional types of subgroups that are normal. Okay, now having defined normal subgroups, we can go into the definition of a factor group. Let N be a normal subgroup of G, and let G mod N be the set of left cosets of N, i.e. The equivalence class of A can be written as an, which is defined as the set of a little n for n in n, where A is any element of the group G. Each A is an equivalence class under the relation A equivalent to B if A inverse B is an n. Okay, so that's the set. We have the set of cosets, and this is something we already explored in proving Lagrange's theorem. But now we're going to put an operation on the set. So we have AB equals AB is a well-defined operation. In other words, AN BN points me to ABN. Okay? And what do we mean by saying this is a well-defined operation? Well, the idea is that this equivalence class, I could take any element of this equivalence class and I might arrive at something different. So let's say we took instead C times D, C and Dn, then we would get CDN. Okay. And so I have to prove that these two things point to the same coset. So we're assuming here that C is equivalent to A and D is equivalent to B. So how can we show this? Well, if C is equivalent to A, that means that A inverse C is an n, or in other words, C equals AN for n in n. Okay, and similarly, D is equal to Bn for B, let's give it a different letter, Bm for m in n. So let's see what happens when we plug this in. So we get CDN will be then equal to AN BM n. Okay. Well, I can insert B inverse here without changing what this means, because this is just the identity. It doesn't change the value of the element of the group. And then this, well, that's why I can insert it, because it equals the identity. But then by associativity, I can also refer to this, AB, B inverse NB, MN. So this, we already said, is an n. And this, because it's the conjugation of an element of the normal subgroup, is also an n. So let me move this out of the way. So this is equal to ABN, which is exactly what we wanted. Okay? So that explains why this operation is well defined as long as we're looking at a normal subgroup, right? And it's key here that this is in our subgroup. If it's not in the subgroup, then there's no reason to believe that we would get the same coset if we were multiplying different representatives. Okay? And let's see what happens in that case. So if we have H, a subgroup of G, which is not normal, and we're trying to do the same thing, so if we have A and B, and we claim this will be equal to AB, but then given So if this is how we're trying to define our operation, then if we take some H in H, we know that H should be equal to the identity class, right? Because if you multiply the subgroup by an element of the subgroup, you still get the subgroup by closure. And using this operation, if we multiply on the left, we find that AH will be equal to A. Okay, but if we're talking about, oh, sorry, let's actually do this on the right. HA equals A. So what this tells us is that HAH will be equal to AH, and in particular that A inverse HAH equals H. But there's no reason to expect this to be true unless A inverse HA equals H, which would mean that H is normal. So there's no reason that, so if we're going to have a multiplication, a group operation satisfying this rule on the set of cosets, we really need this normality. It's going to fall out by force. Okay, now let's look at the order of a factor group. So let's say we have n in G, and we're looking at the factor group G mod n. So this will be equal to the order of G divided by the order of n. And this isn't hard. You can just recall the proof of Lagrange's theorem. Cosets have equal size, and they partition the set. Okay, so because G mod n is just the set of cosets, that means that it's the set of cosets. This is the, and then you take, since each coset has size n, so the number of cosets times size of coset will be equal to the group, the size of the group. And this is just size of n, and this is size of G mod n. Okay, not too difficult. Okay, I'm going to prove Cauchy's theorem for abelian groups. And it's true for all groups, but we're just going to prove it in the case of an abelian group. Let G be an abelian group. If P prime divides the order of G, then there is an element A not equal to the identity in G, such that A to the P equals E. In other words, the order of A equals P. Okay, so the way that we're going to prove this, we're going to try and prove it by induction. By induction on the size of the group. Okay. In particular, you can, if the size of the group is just equal to a prime, then you know that it's the cyclic group, because as a consequence of Lagrange's theorem, this is the cyclic group of size p, so it has an element of order p. So this is a cyclic of order p, so that works. This will be kind of like our base case. Okay, now suppose, now we're going to do the induction step. Take G of order n. Suppose our statement is true for all smaller groups. Okay, so we're going to prove it's true for G. Okay, and let's break down how we're going to do this. So we start with G, and we have something like a decision tree here. Okay, so the first thing we look for is a proper subgroup of G. Okay, so is there n proper subgroup of G? That means it's not equal to the identity or the whole group. So recall that if G is abelian, this is actually a normal subgroup. So, so we can write normal. So if there exists such a subgroup, that's one case. If there's no such subgroup, then we know that because we would expect to have a cyclic subgroup and none exist, so this means that no subgroup exists means that it's cyclic of prime order. Okay. So if it's cyclic of prime order, we're done, because then we have then the prime dividing the order of the group is the order of the group, and we have a generator of the group. So this case is done. Okay, so if we do have a subgroup in G, which is proper, so we have two cases. Either P divides the order of n, or P does not divide the order of n. Okay, so if P divides the order of n, then this is a smaller subgroup. It's abelian. It's a smaller group which is abelian, and the prime still divides the order of it. So that means that there's an A in n with A not equal to the identity and A to the P equals E, so we're done. Okay, if P does not divide n, this is the trickier case, the order of n, I should say. This is a trickier case, so then we have to pass to the quotient group, or the factor group. So G mod n is smaller, so there's going to be a class is smaller with P dividing the order of G mod n. And the reason that's true is basically from here, right? If P divides G but does not divide n, then when you divide out the order of n, you're still left with a factor of P. Okay, so we've satisfied the hypothesis of the theorem of the induction hypothesis, which means that there exists an A, and we'll write it as an equivalence class in G mod n, such that A is not equal to the identity, or the class of the identity, but A to the P is equal to the class of the identity. What this tells us is that A is not in n, but A to the P is in n. Okay. So once we have that A to the P is in n, we know that given any group, if you raise an element to the power size of that group, you get the identity. So take, if m is equal to the order of n, then A to the P to the m equals E. And we know that P does not divide m, right? Because that was stated up here. So this tells me that I can swap the exponents and keep it the same. So that means A to the m to the P is equal to E. And since P does not divide m, we know that A to the m is not equal to E, since P does not divide m. And we know that the order of the class of A is P. So that means that we have our element, A to the m works. Okay, so it's this big induction. And this is kind of how a lot of proofs in group theory go. You assume it's true for smaller groups, and then you can either use a subgroup or you can quotient out by the subgroup. And one of those two things will do what you are hoping for it to do. Okay, now before we finish up, we'll look at another perspective on quotient groups. And this perspective is to focus on the equivalence classes. Which elements are forced into equivalence by the map to the quotient? So for instance, if we're looking at the subgroup 4z, so these are the multiples of 4, as a subgroup of the integers, we can think of this quotient of the quotient group z mod 4z as cosets that are now forced to be identified. So we have our equivalence classes 0, 1, 2, 3, and sitting on top of those you have every other integer. So here you have all of the integers of all of the multiples of 4. Here you have everything plus all of the integers or multiples of 4 plus 1. And same as here, 6, 10, 14, etc. Seven, 11, 15. And so instead of just thinking about 0, 1, 2, and 3, you can think about all of these elements of the integers being tethered together in this class. Okay, let's look at another way, another application of this perspective. So if we have the integers as a subgroup of the reals under addition, so what does that look like? We have the integers and we have the integers sitting in the real line. But when we identify, so when we take the quotient of R mod z, we're saying that anything whose difference is an integer are now the same. So we're going to associate this element to this element to this element to this element, etc., going off to infinity. This element to this element to this element, etc., and you get the idea. But we also get that the integers are all identified. And one perspective on this would be to think about all of this as living on a circle. And with each turn of the circle, you get a new integer. Okay, so we'll use pink because that's what we used over there. So so the equivalence relation is really kind of taking a projection of this spiral, of this helix, and projecting it down onto the circle. So we have all of these are now identified. And similarly, if you take a third and 4/3 and 7/3, etc., now these are all identified. Okay? And so when we think about this quotient group, we're kind of curling around R and then squishing it together into a circle. Okay, how about the normal subgroup of the multiplicative complex numbers and the normal subgroup of numbers whose norm is 1? So what do we think about the quotients here? So let's draw a complex plane. Okay, so we're going to omit the we're going to omit the 0.0. And we're saying basically that two numbers are equivalent if their norm is the same, right? So what does that do for us here? So if we have the unit circle, that's our subgroup. So we'll take this, and we can just kind of, because we're considering all of these the same, let's just call it by its positive real norm. Okay, but then every other subgroup, because it's just, you can multiply, two numbers will be the same if their norms are the same, right? So it'll just be another circle. Okay. Similarly out here, oh gosh, it's becoming less circular as we go on. Okay. And so what you can see here is that the way the quotient works in this instance is that C cross mod this normal subgroup N, rewrite that, is really isomorphic to the positive reals under multiplication, right? Because every coset, every equivalence class here is identified with a circle with a fixed norm. And if I take, let's say I take two complex numbers, r e to the it and s e to the iu, okay, remember the group operation is multiplication, so what I would get is r s e to the I t plus u. So we still get these radii multiplied together. So if I were to just ignore what's happening in terms of the modulus, not modulus, in terms of the argument, in terms of the where in the complex plane it sits, and just focus on its radius, what we would find here is r times s equals rs. And that's exactly the group of positive reals under multiplication. Okay, so that's a look into factor groups, and hopefully it helps with the exercises. I'll see you on Monday.